Hello everyone. Today I'm going to show you a proof that the square root of 2 is not rational. We've seen a lot of proofs of this, but today I will show you one using a technique called infinite descent, a technique that was pioneered by none other than Pierre de Fermat. All right, so let's begin with some simple ideas. Here we have a square OPQR, like so. And let's draw a diagonal line from O to Q, like that. Okay, so let's pretend, like usual, we'll do contradiction. So let's pretend the following. Let's say square root 2 is a rational number, m over n. Okay, so m and n are natural numbers, like so. Well, what we can write is this: OQ is proportional to OP. Now, you know how that goes. If this is one unit x, then this is root 2 times some unit x. So this proportionality is root 2 to 1, like so. So if this is true, then I can find a system of units where this is n long. So this is n centimeters, let's say, or n, whatever units I choose to make this exactly n. If I do that, then this will become m, like so. All right. And I will have OQ is proportional to OP as m is to n, and this is the fundamental thing that we're assuming, and this is what will cause the contradiction. So when you take m and n to be integers, this causes the contradiction. So one more time, we choose OP here to be n units long, and if this is true here, if this here is true, and then this and this, then the long diagonal OQ will be m units long. Now, this is a very interesting proof that's coming up because of many reasons. The proof does not use the usual ideas that we see in proofs about square root 2. So we won't be talking about GCDs, greatest common divisors. We won't be talking about divisibility. We won't be talking about even or odd numbers. And we won't be using the fundamental theorem of arithmetic. So none of these things will appear in the proof in any direct way. Maybe in some really indirect way it's there underneath the surface, but I won't be using any of these things directly. So sit back and enjoy this. This is going to be very interesting. Okay, let's go back to our square. Our square is called OPQR. And let me put back that diagonal line as we said before. All right, so OP, we'll call that N here. And OQ, that's M over here. So this long diagonal is little m. And what we're going to do now is draw a circle. Let's see if I can do this. Yeah, that's not bad. And the circle intersects the diagonal on point. Let's call this point P prime. Let me show you a bird's eye view of that. There we go. Okay, so this is N, this is M, here's our P prime, this is our big circle. Notice the circle goes through points P and R, and it's centered on Q like that. So I should have mentioned this, that the center of the circle is Q, this is R, this is going to be R also. Okay, and this is R. Well, R is the same thing as N. The radius of this circle clearly is N, because this is a square, right? So this is, let me use a different color. This is N, and then this has to be N, and this has to be N also, and this too, because it's all a square. So the radius is N. Okay, great. Let me make a bit of room here. So what we're going to do now is draw a kind of perpendicular line here right on point P prime. And I will zoom in to show you that here. So here I've zoomed in on the most important part of that figure. We've got our circle here in green. We've got our point P prime over here. We've got N, and we have M, the long diagonal here. And I've got this perpendicular line. So we've constructed P prime, Q prime perpendicular to OQ, and Q prime here is the point of intersection of this perpendicular with OR. So I've created this point Q prime. Now, why did I do that? Well, if I draw this in a bit, it looks really suspiciously like a square. Yes, like a little square. Yeah, and so that's what I want to prove. So in fact, I want to prove the following, that this Q prime R is the same segment length as this Q prime P prime, and it's the same as this. Okay, so that's going to be an interesting job. So my first task is to prove that these two are equal. OP prime is equal to Q prime P prime, or P prime Q prime. Okay, that's easy to prove. So OP prime is a diagonal of a square, okay, of a square. So that means this angle is equal to this angle, so it has to be 45 degrees. But this is 90, so this has to be 45 degrees also. So therefore, this triangle OP prime Q prime, is isosceles. It's iso. And so therefore, the two legs have to be equal. So OP prime is equal to OQ prime. So I'm justified in putting these two lines here. Okay, so now I want to prove the following. Q prime R is equal to Q prime P prime. So I want to prove the following, that this here, Q prime R, which is this length here, is equal to this length here. Now, how am I going to do that? First, let's draw this line. Okay, so draw Q prime Q. Okay, so the two triangles here, triangle Q prime R Q and Q prime P prime Q. Let me use some color and show you. This is the first one, triangle Q prime R Q, and let's use a different color. This one here, that's Q prime P prime Q. Okay, they share a side, and that side is Q prime Q. They share the hypotenuse. Also, they have some angles that are the same. These two angles are the same. So those two angles here, Q prime RQ and Q prime P prime Q, that's this angle here and this angle here. They're both 90 degrees and they're the same. But I have one more thing. This side is equal to this side because this is a circle, right? So these are radiuses. This is N and this is N, from here to here, okay? All right, so let me write that down. Like so. So all of this information all together, with these angles and sides being the same, well, the two triangles are congruent. There we go. And so we are justified in saying that this segment here is exactly the same as this segment here. So therefore, I can say now, like so, Q prime R is Q prime P prime. It looks like a mess here, but okay, let me let me start over here. Okay, let's make it look a bit better. I can remove all these construction lines. What we've proved now in total is that this equals this equals this. Okay, so it's going to be easy to make a square. We can finish a square by putting two more segments like this. And we will need this segment. We'll need to know that this one is equal to do some magic a little later on. Here's what I mean. So I have added this point here, r prime, in order to do the following. To complete the little square O, P prime, Q prime, R prime, which you see here. Okay, so it is possible to make this square because we proved that this here, this segment is equal to this segment. And so, of course, we can construct the other two segments to be equal also, and we get this little square. Okay, so what we have done is a transformation. We transformed the big square OPQR to the little square OP prime Q prime R prime. And thus we also transformed these dimensions. This is n and this is m, the long diagonal. We transformed that into little n and n prime, and little m prime, this long diagonal of the little square. So we transformed from n to n prime and from m to m prime, okay, where they seem to get smaller. Okay, that's a critical observation. So let's calculate this transformation of these dimensions. All right, so first of all, n prime is equal to, that's this thing here. That's the same as OP prime, okay, but I can rephrase that as the long diagonal minus the long diagonal here. Let me mess this up. The long diagonal here minus this piece here. All right. So that's OQ minus P prime Q. All right. And this is easy to figure out. Now, OQ is M and P prime Q is, well, that because P prime Q is a radius, so it's the same as this here. This is also a radius, that's n, so there we go. So we've got the first transformation done. Now let's do the second one. M prime, that's OQ prime over here. Let me colorize this over here. All right, but I can do the same sort of trick now. This is OR minus RQ prime. And now we use what we discovered before, that this equals this, and this is N prime, like so. So this is N minus N prime. But we already know n prime, so this becomes n minus m minus n, and that's 2n minus m. So we have our transformation formulas. The new diagonal is n 2n minus m, and the new side is m minus n, like this. Okay, so this is our transformation. There we go. Okay, so that's very interesting. And now we want to prove some facts about this transformation. We can deduce some properties of this transformation from the figure. First of all, m prime and n prime are not negative, and they're not zero. They get smaller, but they never hit zero. I mean, no matter how small of a square you start off with, as long as it's a finite size, the little square will be smaller, but it's never going to be zero. So from the figure, this is obvious. Also from the figure, it's clear that the smaller square is smaller and will always be smaller. So we have this, that m prime is smaller than m and n prime is smaller than n always. And let's refresh what we mean by n and n prime and all that. This is n prime, this is n, this long diagonal is m, this long diagonal of the square is m prime. So, okay, these things are kind of obvious from the figure. We can prove them using some algebra. Is it really necessary to prove it? I think this suffices as a good argument, but let's prove it anyway. So we're going to consider this triangle here, OPQ, like this, and we will apply the triangle inequality to OPQ. and see where it goes. So OP is less than OQ. The side is less than the hypotenuse, than the long side of the triangle. Okay, that's true. And that's less than the long side, the hypotenuse is less than the legs combined, and that's the triangle inequality. So that's true. So written in terms of n and m, I have this. Remember that PQ is also n because it's radius, and RQ, might as well write that. That's also n. So I subtract n from this, and I get the following, like so. All right, so I have proved that this is n prime, so I have proved this is done and this is done. Okay, so I have those two down pat. Now let's take these two here and let's rearrange this a little bit, and we get 0 less than 2n minus m, but that is our transformation m prime here. So I have this one is done now. I just have one left. I have to prove this one here. That's not so hard. We'll start with the property of triangle. N has to be less than the diagonal m. And so I have that. And then I subtract an m from both sides, and I get this. And this is m prime. Okay, so I have m is greater than m prime, and I'm done this. So I have all these properties. Okay, let me make a bit of room and summarize all these results in a nice table. First of all, they get smaller. The transformed square dimensions are smaller than the original square, and they are always positive. So no matter how small a square I start with, I will always get a smaller one, and it will always be positive, never become 0, strictly positive. So it's not the negative that's the issue here. It's the fact that it never becomes 0. That's the interesting thing. All right, so this is what we need, the key to constructing the infinite descent. If we can apply that transformation once, well, there's nothing stopping us from applying it again. So the first application of this transformation gives us a smaller square here, and a second application will give us an even smaller one. Let me show you what I mean. So this was my big outer square, OPQR, and then this one here, OP prime, Q prime, R prime was the smaller one that we created. But now let's apply the transformation again. So we now put a circle on Q prime instead of Q, and we get a new point here, P prime prime, and we will construct the perpendicular line in the same way, and we get the following. Very nice, and I'm sure you can see that here I can add a point R prime prime and construct a square like that. So let me show you what the finished product looks like. There we go. All right, so this was n prime, and this diagonal was m prime, and now we transform n prime and m prime into new smaller versions. This is m prime prime, and this is n prime prime from O to P. So I can write this down. N prime prime is OP prime prime, and m prime prime is OQ. Let me write that better. OQ prime prime, like that. Okay, so we apply the transformation. We now start with n prime and m prime, not with m and n, but n prime and m prime. Okay, so this was our general transformation, but now we are not beginning with m and n, we're beginning with m prime and n prime. So we have the following, like so. Okay, this is n prime prime. Okay, and furthermore, the new m prime prime must be smaller than the old m prime, and the new n prime prime must be smaller than the old one, m minus n prime, like this. As an exercise, find m prime prime and n prime prime, compute them in terms of m and n, the original big square dimensions. It's an easy exercise and it's quite interesting to do. And now for infinite descent. We can keep applying this transformation. We start with a square of dimensions m and n, where m is the long diagonal and n is one of the sides, and we can keep applying. First application gives us this. Second application gives us m prime prime n prime prime. Another application gives us m prime prime prime, m n prime prime prime, and so on and on and on. And these things are all positive because we proved that every transformation application always results in positive numbers, decreasing positive numbers. Since m and n are both natural numbers, that's what we assumed at the beginning. These are two sequences, this one and this one, sequences of integers, and they have the following properties. They are infinite sequences because the geometrical construction can go on and on forever. They are strictly decreasing. And so if I have, for example, mk, this is going to be greater than the mk plus 1th application of the transformation. And then also nk is going to be greater than nk plus 1, like this. We proved these things earlier. And they're bounded by 0 from below. We proved this because we proved that every step in these constructions leads to positive integers. And this is, n, and k is also positive. All right, so this is impossible. This is a contradiction. You cannot have a sequence of integers that's infinitely long and positive if you begin with an integer that's finite. Of course, these two are finite. So that's a contradiction, and this is infinite descent. This is very interesting because it shows you that root 2 cannot be a rational number, but I think it also gives some insight as to the nature of root 2 that perhaps the other proofs don't really address in some way. So you think about it, it's very interesting. As always, like, subscribe, and comment. Let me know what you think about this proof of square root 2's irrationality. All right, and I want to make a few comments before I leave you. What if you try talking your way out of this? For example, let's say you say, well, okay, I make this construction, but sooner or later, the squares kind of go on top of each other, and, you know, they're all coincident, and then therefore the sequence kind of terminates. Well, that's impossible because we proved that the next step is always smaller. So they're never on top of each other. The dimensions of the next one are always smaller. And what if you try arguing like, there's an infinite number of integers, you know, they can go on, and eventually these subtractions and, you know, like 2n minus n, you're going to get a 0 or below 0 or something. And so, you know, it can go on to infinity in the negative direction. No, because we proved that m prime and n prime are always positive. And what if you argue that, but what if m and n are infinitely big? Then there's enough room for this infinite descent to fit in. It'll work. No, because we assume that square root 2 is a rational number, m over n. So that's two finite integers. You know, you can't make a rational number by dividing two infinite things. Okay, so no matter how you try talking your way out of it, you won't. Okay, that's the brilliance of Pierre de Fermat. I think this is the best example of infinite descent that I've ever seen, and I hope you like it, and I will see you next time.